Okay, I think we're going to get started. I see a few people have already joined. Me, Sam, hi, good to see you this afternoon, evening. I'm in a slightly different room, so I apologise if there's a little bit of echo, but hopefully all of you can still hear me well. Inga, hi, good to see you. Hope you're well. Hope you've had a good day. Thank you for being our lovely moderator, as always, this week. Before we actually get started, I'm not actually around next Wednesday, so I just wanted to ask, can we do this on Thursday? Does Thursday work? Hopefully it does. I think I'll try and get an email sent out in advance, but I think I might have to move the squad to Thursday. I actually have an exam next Wednesday. I don't think I'll be back in time from the exam hall by 5 o'clock. So, yes. So if we can move it to Thursday, that'd be great. As always, just wanted to draw all of your attention to a few things. Number one, make sure you check out the other squads that happen in the week. They're absolutely brilliant and they are carried out by absolutely wonderful content creators. Really, really talented, really, really knowledgeable. So please do check them out. Also, do check out my other videos from the squad series from both this one and last time's one. Last time was all about study skills, and this time is all about chemistry. Also, towards the end of the squad, there will be a survey link that Inga will kindly put in the live chat. It is super, super important that you fill in that survey, that feedback form, because it does help me as a tutor conducting these squads. It helps me know what I could do better and what you guys like. It also helps my tutors so that when we continue rolling these out, we know what to improve on and we know how to make it the best experience for you guys as possible, because we're all here to make sure that you guys can be the best students that you can be. So any feedback on what we can do to make the experience better, whether it's slightly longer sessions for next time or whether it's sending you questions and stuff afterwards or in between sessions, whatever we can do, you just let us know, give us as much feedback as possible, because it's always really, really useful. But otherwise, how is everyone this evening? I see loads more people joining, and I want to see loads of engagement in the chat this evening. So do say hello, either just a bit of a wave or an emoji or something like that. Do say hello. I want to see lots and lots of engagement this evening. Today we're going to be going over reversible reactions and dynamic equilibrium. So going to be another sort of crash course lesson, kind of going through the fundamentals. And hopefully all of you have got your chemistry hats on. Or I should say your chemistry crowns on, because you're all chemistry kings and queens and we are the best squad that is out there at the moment. You can't hear me? Oh, interesting. Okay. Can all of you hear me or not? Hopefully you can. My microphone's picking up sound, so it's interesting that you can't hear me. So Charlie, you can hear me. Mewish, maybe just double check that you're not muted. But sometimes computers do really weird and wonderful things, so just double check your sound, okay? But great that everyone can hear me. Hi, Angel. Good to see you as well. Charlie, I think I've already said hello. Hi, good to see you again, mate. Great to see all of you here. We're just going to get started in the next 2 minutes or so. How's everyone's day been? Hopefully it's been okay for everyone. I'm just drinking, I think, my third coffee of the day in my good old Dragon Ball Z mug. One of my friends at university got this for me for was it my 20th birthday? It was my 21st? Yeah, because we're students, so we've not got loads of money. Good to hear that your day was good. Mine was okay, very busy as always. As all of you know, I'm a hospital pharmacist, so at the moment I'm based in hematology and oncology, and today was really, really busy because we basically have all three clinics, both breast, lung and hematology, and I had to get through loads and loads of prescriptions and blood results to get through, so lots to do today. But like I always say, I've got an absolutely amazing team that I work with. They're all really, really supportive, so I've got no complaints. It was a very productive day. Um, but no, good to hear that you've had a good day. Absolutely fantastic. Oh, dearie me. It's been a long day, I will say that much. Do I make the medicines? So some hospitals will make the intravenous chemotherapy. Um, we don't. So we actually outsource. So we have like manufacturers that will make it aseptically. What I do, what my role is I look at the prescriptions after the doctor's prescribed them, and I basically make sure that they're safe, the dose is correct, that the patients can have the certain medications based on their blood results. So I'm basically what we call validation or screening. That's what I do. So I do a lot of coordination. I order a lot of the chemotherapy also. So um, my role is quite varied, and sometimes I'll also speak to patients about their medication, make sure they understand what they're taking. If they've got any questions, then I can answer those as well. So I do a variety of things on a day-to-day basis. Um, it's never a boring moment, I suppose, is probably the best way of putting it. Um, but no, good question all the same. Hey, Lyrics, good to see you this evening, mate. I hope you're well. Great to see you again. Great to see you join. I think we can just get started, really. I think we'll just crack on with it. So, today we're going to be going over reversible reactions and dynamic equilibrium. Now, my first question to all of you is, it was Pancake Day yesterday, and what I'm saying is it's definitely relevant. It's not a tangent. I want all of you to tell me what the ingredients are for making pancakes. Okay, not a trick question. I want you to tell me what are the ingredients for making pancakes, assuming you made pancakes yesterday, or even if you didn't. So I want to see loads and loads of responses, guys. What are your ingredients when it comes to making pancakes? This is related to dynamic equilibrium, I promise you. What are some of the ingredients? Don't be afraid to use good old Dr. Google if you are unsure. Okay, we've got an answer from Angel. Milk, eggs, and flour. Very good. Michaela, good to see you. Eggs, flour, and milk as well. Yeah, no, good. I think that's pretty much it. Actually, this is where I'm exposing that I don't I don't make pancakes very often, at least not from scratch. You might add other things like sugar, maybe chocolate, but yeah, those are your fundamentals. Very good. Now, the reason I ask that is that when you take in your eggs, your milk, and your flour, you've mixed it all together. Okay, you made your batter and you put it in the frying pan. You made a pancake. Can you then reach into that pancake and then take out the eggs, the flour, and the milk? Can we separate them? There should only be one correct answer that I see in the chat, so I want to see the one answer. There's only one answer. Can you reach into your physically made pancake and take the ingredients out? No, you can't. Well done, guys, you can't. And this is because making pancakes is what we would describe as a unidirectional process. It only goes in one direction. No music pun intended at all. Now, what I mean by that is that there are some chemical processes that also go in one direction. Here's another example that's more chemistry related. Let's say, for instance, I was looking at the combustion of carbon. So generally I know that carbon, when burned, produces carbon dioxide. Okay? So I know that this is another example of a unidirectional process. With combustion, okay, it only goes in one direction. There is no way for me to feasibly then look back at what I've produced. Okay, there's no way for me to take all the carbon dioxide gas and then somehow reform the carbon and oxygen respectively. It's not possible. So the point that I'm making is ultimately some reactions only happen in one direction. Okay? And in those types of chemical reactions, we generally represent them with a single-headed, a double-headed arrow, but it only goes in one direction. And we've shown that here, okay? On the other hand, there are other types of reactions which do go in two directions. And the example that I'm going to use is I'm going to use the Haber process, because it's a classic example of a question that you get in your exams. It always sort of comes up. So I'm gonna use that as an example. And the arrow looks like that. Okay, so this is what that looks like. Okay, and this is an example of a bidirectional reaction. Okay, so that's what we've got going on there. Okay, so it's a bidirectional reaction. Okay, however, a better way of phrasing that would be it's a reversible reaction. Okay, now has that made sense to everyone so far? Okay, has that all made sense? Thumbs up in the chat if it has made sense, thumbs down if it hasn't made sense, or smiley faces or frowny faces. Just want to make sure we're all on the same page at the moment. So Marish, you've asked what year is this topic? Well, the series is catered towards GCSE, so year 10, year 11. Some of you may have started your GCSE content in year 9, but around that age group, so key stage 4. Cool. Okay, so it's made sense so far. Fantastic. Great to see. Now, this is an example of a reversible reaction where your reactants can go on to form products, and your products can then go back to reform reactants, depending on the circumstances. Okay. Now, the reason that I use the Haber process, where hydrogen and nitrogen go on to form ammonia, and actually, now that I think about it, this is not a balanced equation at all. Let me balance that out. Now that's balanced. The reason I picked this is because this is the way that we make ammonia, and ammonia can be used to make a variety of things, like fertilizers and bleach, for instance. So it's a really, really important product. Now, in chemistry, when we think about reversible reactions, we also have to think about the conditions under which the reaction is reversible. So this is where we're going to introduce the idea of an open system and a closed system. I want all of you to sort of think, what do you think an open system is, and what do you think a closed system is? What do we think? I'm going to write that in the lesson space. Ardell, hello, good to see you. Great that you were able to join this evening. Hope you're well. So we have an open system, and then we have a closed system. So I'm going to do that. So what do we think? What's the difference between an open system and a closed system? Okay, so Ardell, you've said a closed system is where nothing can get in or out. And when we say nothing can get in and out, what are we referring to? Misan, you said a system that can be used anyway with something that's opened. Ardell, you then followed up with energy. Yeah, so Misam and Ardell, you're on the right lines, okay? You're in the right direction, okay? Open systems are those where energy and matter, and I suppose arguably the two are interchangeable, can be exchanged between the system and the surroundings, okay? So generally in this context, we're thinking about reactants that can move between the system and the surroundings. A closed system would be where the reactants and the products are separated from the surroundings, so there is no transfer. Now, the reason this is important is that reversible reactions can really only exist in a closed system. So I'm going to put a tick next to closed, and I'm going to put a cross next to open. And the reason for that is that in a closed system, your reactants and your products are sealed away. So when your reactants go on to form products, your products can then go back and reform reactant. But if you have an open system, when your reactants go on to form your product can then escape, if it's a gas, for instance, and then go out into the atmosphere, where then you no longer have that product to then reform your reactant. So if you had this reaction mixture in a beaker and the beaker was open, there was no cover on it, then your product could then go, it could what's the word I'm looking for? Diffuse into the atmosphere, and you don't get it back. Okay, so a reversible reaction doesn't work in an open system, it only really works in a closed system. Okay, does that make sense as well? Are we all on the same page on that front? Yeah, quick thumbs up in the chat. Want to see loads and loads of thumbs ups or smiley faces or anything that is PG in the chat, just to signify that we're all on the same page. Fantastic. I see a thumbs up from Angel, thumbs up from Michaela, yes from Ardil, Thumbs up from Charlie. This is fantastic. You're smashing it, guys. Really proud of you. Well done. Right. So we've talked about open systems and closed systems with regards to reversible reactions. So now, and Misam has asked, yes, could you tell us the definition of a closed system? So I would say a closed system is where your reactants and your products cannot be interchanged with the surroundings. So your reactants and products can't interact with the surroundings. That's what I would say a closed system is. Now, if we then think a little bit about the idea of a reversible reaction, we can then put this in a graph form, okay? So this is where I'm going to expose that I cannot draw for my life, but I'm going to sort of sketch some axes, okay? Now on these axes, the red line is going to represent my formation of product, and the blue line is going to represent my loss of reactant. And I use the word loss. Oh God, there we go. I use the word loss very loosely because, as we know from the law of conservation of mass, energy is never created or destroyed; it's only transformed. So this is what your graph might look like, okay? And this should make sense because in the case of your red line, at time 0, you don't have any product because your reaction has not started. But then what we know is that the rate of reaction is going to be very, very fast initially because that's when we have the most amount of reactants. We have the most amount of collisions. Your collision frequency has peaked at that point. As time goes on, your concentration of your reaction will go down, and therefore the rate of reaction will also go down. We could also look at the blue line, and the blue line represents the concentration of reactant. So we know that your reactant concentration will be at its highest at time equals 0, again because the reaction hasn't started yet. And as time goes on, the concentration of reactant will decrease. So as a consequence, this will also slow down. Okay, does that graph make sense to everyone? Yeah, quick thumbs up in the chat if it does. I want to make sure that this graph makes sense because I know graphs can be really challenging sometimes. And anytime I've marked papers, I always find that it's graph questions that trip up a lot of candidates. So I want to make sure that everyone is on the same page and everyone understands the graph that I've just drawn. I'm just going to change this to blue, just for consistency. There we go. Yeah? Okay, fantastic. More thumbs up. Great to see. Okay, so that's what we've got going on here. Now what I want to focus on is I want to focus on this line here, which I'm going to draw in green. Okay, so this line here. Now at this point, your lines have sort of balanced out, right? They've kind of plateaued. And on a graph of concentration against time, we know that the gradient is rate. So this is the rate of reaction. And so the fact that your curves have plateaued would suggest that the rate of reaction has now become constant. At this point, we can say that the reversible reaction has reached what is referred to as dynamic equilibrium, and this is the magic phrase for today. Dynamic equilibrium can be characterized in two respects. The first respect with dynamic equilibrium is that the forwards rate of reaction equals the backwards rate of reaction. Okay, so they are exactly the same. This is the first point about, about dynamic equilibrium. Okay, that your rates of reaction have effectively become one and the same. Okay, the second point about reversible reactions is the fact that, or with dynamic equilibrium, is the fact that there is no overall change, but the reaction is still going on at a molecular level. And this is quite important to remember, because whenever we think that the rate doesn't change, I think we have a tendency to think that the reaction has stopped, but we know that the reaction hasn't stopped. In reality, the reaction is still going on, but we just don't see an overall change. Now, in fact, you know what? I'm going to move these across because I don't think you can see that very well. Now, for us, what that would then suggest... Oh, okay, so Adu, you've actually given the definition. Fantastic. During dynamic equilibrium, the reaction is not stopped and the rates of reaction are a constant, which means they cannot be changed. I'm actually going to, well, they can't be changed under normal circumstances. That's correct. So that's a really good definition there. Well done, Adil, for commenting that. And this is where we're now going to move on to the idea of reversible reactions, and where we're going to talk a little bit about the Châtelier's principle. Okay. Now, Le Châtelier's principle relates to the idea of dynamic equilibrium. Okay. With dynamic equilibrium, we have said that it's characterized by two specific things. The first is that the forwards rate of reaction equals the backwards rate of reaction. They are now constant, not change. The other point is that there is no overall change, but the reaction is still happening at a molecular level. So those are your two things. So we can think of dynamic equilibrium almost as a state of balance. So what then happens if we disturb that balance? Well, this is where Le Châtelier's principle comes in. Now, I want all of you to tell me what Le Châtelier's principle states. Okay? I don't necessarily need the exact word for word definition. I just want to see what you understand in your own words. Okay, so Le Châtelier predicts a change in an equilibrium position if the conditions of the reaction are changed. Good. So that is the definition of Le Châtelier's principle. In essence, it lets us know how exactly the equilibrium will shift to counteract a change. Okay? So whatever we do to the equilibrium, the Châtelier's principle tells us that the equilibrium will then do the opposite to counteract the change. And in this topic, there are 5 different factors that I would say you always get tested on. So there's temperature, there's concentration, there's pressure, there's catalysts. In fact, I might be wrong there. I think it's just 4. I think it's just the 4 because surface area isn't relevant here. Okay, so these are your different factors that you tend to be asked about when it comes to dynamic equilibrium and the Châtelier's principle. Now, before we go any further, I need to stress that this is not the same as a rate of reaction. The rate of reaction refers to how quickly the reaction occurs. So, whether or not the collision frequency increases. Le Châtelier's principle looked at the position of the equilibrium, i.e. what the yield is going to be. Now, Ardo, I know you said no catalysts. Catalysts tend to be asked about, but that's a trick question, but we are going to get onto that. Okay, I've purposely included that one because that's one that always crops up, and I think throws a few candidates off. So we will talk about that one as well. So let's start off with temperature. Now, when we think a little bit about the Châtelier's principle, specifically with the Haber process, what we sort of think about are whether the reaction is endothermic or exothermic. Now, in the Haber process, the forwards reaction is exothermic. Now, we know that an exothermic reaction is one in which heat is given off, transferred to the surroundings. An endothermic one is then where heat is taken in. So if we look at this specific example, we can say that the forward reaction causes an increase in temperature, the backward reaction causes a decrease in temperature. So if I was to then try to increase the temperature of this reaction, the equilibrium will try and counteract that change because that's what the Châtelier's principle stipulates. So in your exam, always say, the Châtelier's principle states that whatever you do to the equilibrium will counteract the change. Therefore, if I increase the temperature, the equilibrium will then shift to try and decrease the temperature. So it will favour the endothermic reaction by shifting to the left. And Ardil, you've pointed out the opposite, that if temperature is decreased, then again the Châtelier's principle will try and counteract that change, and therefore try and favour an increase in temperature. So it will shift to the right, which favours the exothermic reaction. Okay, I think what's key when it comes to the Châtelier's questions is always pointing out the direction that the equilibrium shifts, and also pointing out, and just even just stating the Châtelier's principle, because it gives you a nice foundation to work with. Okay? Does that make sense for everyone? Hopefully it does. Give me a quick thumbs up or a smiley face in the chat if it makes sense. Hopefully that makes sense to everyone. Is the equilibrium the green line on the graph? So Misam, the green line, anything after that, I just sort of cut that down there just to sort of show that beyond that point, the curve plateaus. So beyond that point is dynamic equilibrium, yeah. Yeah, good question. But yeah, that's what that refers to. Yeah. Are we all okay then? And then if so, we'll speed through the remaining ones. Yeah, quick thumbs up if we're all on the same page. Okay, I think we're good. I've not heard any thumbs downs, or seen any thumbs down, I should say. So I think we're all good. So we'll just keep moving. Let's look at concentration. So again, when it comes to the idea of concentration, the Châtelier's principle stipulates that if I were to do something to the equilibrium, it will then shift to the left or to the right to counteract that change. Now, with these questions, it's always important to look at how much reactant and how much product you have on both sides. So on the left-hand side, I have 4 moles of product, because I've got 3 moles of hydrogen and 1 mole of nitrogen. On the right-hand side, I have 2 moles of ammonia. Therefore, I can say that there's a greater concentration of reactant than there is with product. Therefore, what I can say is that if I try to increase the concentration of, let's say, nitrogen, equilibrium will try and counteract that change and try and decrease the amount of nitrogen. And it will do that by favoring the forwards reaction, because the forwards reaction involves using up nitrogen. Okay, so that's what I would say in that regard. Okay, similarly, if you wanted to try and, let's say, you decrease the concentration of ammonia, the equilibrium will try and counteract that change. We're trying to increase the amount of ammonia. Again, this would probably involve shifting to the right, because the forward reaction involves forming more ammonia. Okay, I think there's a little bit of lag there, but I think we've stabilized. I think we're okay. Misam, you've asked, do I know if it's paper 1 or paper 2? Which exam board? I think for AQA and Edexcel, actually. I think this falls under paper 2. But I would recommend popping on your exam board website and then just double checking. I think that with AQA and Edexcel, it's paper 2. And then, if we then look at pressure, so again, this is quite similar to concentration. Again, when you're looking at gases, look at the number of moles you've got of each thing. So on the left-hand side, we've just said we've got 4 moles of gas. On the right-hand side, we've got 2 moles of gas. So what we can say here is that the left-hand side has a greater pressure than the right-hand side. So in light of that, what we can then say is that if I try to increase the pressure, equilibrium will try and counteract that change by trying to decrease the pressure. So it will shift to the right, because the right-hand side has fewer moles of gas, so it's got a lesser pressure. And finally, with catalysts, I'm going to end on a question. Do catalysts affect the position of equilibrium? I've kind of already alluded to this, because I said it was a bit of a trick question, but I want all of you to give me the answer in the chat. Do catalysts affect the position of your equilibrium? Not the rate of reaction, the position of equilibrium. I already have a no from me, Sam. Anyone want to add to that? What do we think? What do we think, guys? I'll give you guys 1 more minute or so to answer. Don't be afraid to answer. We've already got 1 answer so far. Yeah? Rafi, you said no. Hey, Rafi, good to see you this evening. Thanks for joining. Great. I think we're good. We're on the same page. No, that's right. Catalysts do not affect the position of your equilibrium. All catalysts do is increase the rate of reaction, but in the case of a reversible reaction, it will just increase the rate of both reactions. But that's all that would happen. You wouldn't change the position of it. Fantastic. Well done, guys. You absolutely smashed it this evening. Okay, so this is a nice little summary of reversible reactions and the Châtelier's principle. What I would probably recommend in the run-up to your exams is do some pop paper questions, make some notes as you go along. Before you leave the session today, please make sure that you give us feedback. Inga, thank you so much for putting that link in the chat. Like I said before, these sessions are for you guys. Without you, there is no session. So please make sure that before you leave, you definitely fill out the form, okay? And I'll see all of you next week. Like I mentioned before, there will be a message that goes out that says what time it will be, but the next squad from me won't be on Wednesday. Hopefully it's going to be on Thursday, because I've got an exam next Wednesday, so I won't be able to join, but definitely Thursday. Next week's topic is all about alkanes and alkenes. So we're going to be going on to a little bit of organic chemistry, and I know that a lot of people hate organic chemistry, so hopefully a lot of you find that really helpful. If you know someone that does not like organic or doesn't get organic chemistry, tell them to join. Send them the link that's in the description of this video. Okay, so that is going to be next week's topic. But I hope all of you enjoyed this week. I will hang around for maybe 4 minutes or so. I'll probably head off at 5:35. So if anyone has any other questions, either about what we've gone over today, about general chemistry, or about study skills, or anything else, then I'm more than welcome to answer them. I will hang around for the 4 minutes or so. Also, because I'm conscious that I don't want to keep Inga here much longer. I don't want the moderator to have to hang around because I can't time keep. But yeah, hopefully all of you enjoyed the session today. It's great to see so many of you. It definitely, it definitely warms my heart, as I'd probably say, to see so many of you engaged and keen about chemistry and keen to really smash out your GCSEs. I think it's absolutely brilliant. It's inspirational, really. Lisa, I have an interview for sixth form tomorrow. Any tips? Congratulations. Well done. I'm sure you're absolutely going to smash it. In terms of tips, I would say if you haven't already looked up some questions, like some classic sixth form interview questions, then I would say maybe look some up to see, get like a bit of an idea. One bit of interview advice I would always give, I've sat in on interview panels before. I've been interviewed God knows how many times. Don't be afraid to take your time in answering the question. Okay, I think one of the things that a lot of people fall into the trap of is rushing to answer a question because people think that an interviewer wants an answer there and then. I don't think that's the case. If anything, I would say that if you take a little bit of time to think about your answer, okay, it shows that you can reflect and it shows you can weigh up pros and cons and think about what's important. You're not just going to waffle. Look at their core values. Think about what it is you want to go to that specific sixth form. What is it that they offer that you're looking for? That's another thing that I would say. That's really important too. If you have any questions for them, then obviously they'll give you room at the end to ask those questions. I know anytime you get interviewed, you feel like you're having to impress them, but it also works vice versa. They want to impress you. They want to say, look at how great our sixth form is. We want you to come here and we want you to show, So if you have any questions for them, then save them to the end, but ask them. Show them that you have an interest. What if you're not sure what to say for a question? That is a very good question. If you're not sure, if you've had a bit of a think about it, and you say you're not too sure, I think you just have to weigh up just be honest and say, I'm not too sure about the question. If it's the case that you're not too sure because you've not understood it, then maybe just ask them to rephrase it. I'm sure they'd be more than happy But I'm sure they would never ask you a question that would stump you so much you can't think of an answer, right? Um, I think the key thing is be honest with your answering, okay? Because interviewers have so much experience, they don't want to sound too rehearsed to the point where it doesn't sound genuine or authentic. They want to interview you for you. You applied and you got the interview in the first place. So they want to see you, they want to meet you, they want to know who you are, they want to get to know you. So be authentic in every respect. That's the advice I would give. I hope that kind of answers those questions. But definitely look at their core values. Look at what they stand for. Look at how you align with those, how you exemplify those. And maybe just have a look at some questions casually this evening. I know you've got your chemistry mark. Okay, so I'll give you a bit of feedback's the wrong word. Bit of motivation. You'll smash it. You'll be absolutely fine. You've been really, really active on these, and like I always say, the more activity that I get from you guys, it's just fantastic. So I have no doubt that you'll be fine. What I would say is treat your mock as if you were doing the real exam, because then that way you can walk out the mock knowing I did my best, and the grade you get is reflective of where you are, and then that then means you can then use that as a tool to then guide your revision. Okay, take time with the questions, underline them, circle them, try and get into the examiner's head. Think, what is it the examiner is asking me for? Has my answer answered this question? Okay, which seems like a redundant statement in itself, but it's not, believe me. I think sometimes, because of the pressure of an exam, it's really easy to just sort of waffle, which you don't want to do. Hope that is a good bit of advice. Hope that's helpful to you. Best tips on GCSE science revision to get a good grade. Consistency. Consistency is key. Continuously revise. I'm not saying do all-nighters. I don't think they work. Don't cram. Give yourself the time to learn and develop your understanding over time. Past paper questions. Mark those past paper questions afterwards. See where you're going wrong. Then keep reviewing your notes. Keep going back and forth between them. And it's just consistency. It's a marathon. That's what I would say. I would swear by past paper questions and note reviewing, because the note reviewing means you understand the content. The past paper questions continuously make sure you understand the exam technique. You put those together and you're in a very good place. I would swear by that. Not that you should swear though. What to do if you complete every past paper? Give yourself a break and redo them. That's what I did at A-level. I printed off every single exam paper I could for my exam board. And then I redid them all to see whether there was a marked improvement. Obviously not back to back, because you remember the answers from the last one. Give yourself like a month break or so. But just continuously practice, I think. But then also just make sure to take a break, right? Because you've got loads of things to juggle when it comes to GCSE. You've got so many subjects. But yeah, just continuously practice. Okay, because you don't want to get complacent. And I actually realised that I've gone I've gone past the time I said I would. If anyone else has any other questions, then by all means, just pop them in the comment section of this video when it does drop on the YouTube channel. Again, you guys have been absolutely fantastic. I will see you all next week. I'm aiming for Thursday for the squad, but I will get my tutor to send out a message. Okay, so you all know. There's so much content to remember, especially for each subject. There could be, there's a lot of content, and I think that's the difficulty with GCSE. There's so much for you to memorize. So it's just the case of, if you give yourself that time to memorize things over time, then you're much better off. Thank you, Ardil. I hope all of you have a fantastic week. Stay smashing chemistry. I'm super proud of all of you. Thanks so much for joining, and make sure to fill out that feedback link. And I will see you all next week, hopefully Thursday. And if we miss next week, we can always catch up the following week after that. But either way, I'll see you all then. Okay? Take care, guys.